What I want to collect for you here on this page is steps that you can follow when dealing with any hypothesis test for a single proportion. So you can use this as a reference sheet to going through a hypothesis test, it is kind of formulaic. There's a formula to follow to make sure you have all the pieces and the evidence. And if it all ties together correctly, you can get to the correct conclusion. But it is about this whole process and seeing all of these steps. So then the other videos, we went through kind of piece by piece and step by step. But here it is all together, and then we'll go through 2 examples here using these steps. So our first step is stating our null and alternative hypothesis. So we'll have this general structure. Again, that null hypothesis is our assumption, so what we assume is true. And then the alternative hypothesis is what we want to prove. And typically in the wording of the problem, they'll say test something or find evidence for something. And what they're describing there is the alternative hypothesis. Now what I drew in the middle here, these are different possible symbols for our alternative hypothesis, and it will just be based on the wording of the problem in terms of which one you'll use. So when you start a hypothesis test problem, in terms of what will be given to you, typically they'll give you wording for the alternative hypothesis. So with that, you'll be able to set up your alternative hypothesis. When you get that out, you'll get an idea of a value for P to go in the null hypothesis. So that's what P with a subscript of 0 represents. It's the proportion from the null hypothesis. And what you'll also be given is sample data. It's important to separate these pieces. So there'll be something about what they want to test or find evidence for, and then they'll describe some sample data, which will lead to a sample proportion coming from some sample size. So those pieces will be given to you. So based on that wording for the alternative hypothesis, you can set up this piece, and again, those numbers should always be the same, and then in the null hypothesis, you'll always have an equal sign. So then our next step was to go about setting up our sampling distribution, but first thing we have to do is check the central limit theorem. So make sure we have independence, make sure we have randomization, and then check success failure. So taking that sample size times that proportion from the null hypothesis, and then sample size times 1 minus that proportion. So Q is just 1 minus that proportion. Once we have that, we can set up our sampling distribution. So we'll have our mean and standard deviation. So the mean is just going to be the proportion from the null hypothesis, standard deviation calculated with those values. And then again, I know I've said this a few times through these videos, here's the calculation for test statistic. I'll show when we get to an example here how it could tie in, but also if you're doing work, you can skip over this step. It'll just kind of depend on which route you go. I'm typically going to go the route of focusing on our sampling distribution, but I'll tie this in since it does come up. Once we have our sampling distribution, then we can go and find our p-value. So p-value is going to be area under the curve. So this is where we're going to need to go use some technology. What we've been using is GeoGebra, but whatever we're using to find area under the curve, we'll go to that to find p-value. So when you're at this stage, you want to double check your alternative hypothesis to see what kind of test are we doing. Right tail test, then you'll be looking for the area to the right of our sample statistic. And then if you're using the test statistic method, what you would use is your standard normal curve, so mean of 0, standard deviation of 1, and then it would be the area to the right of the z-score. And then left tail would be area to the left. And then two tail, as we talked about, there's 2 possibilities. If you're landing on this right-hand side, you'll take 2 times that right area. If you're landing on this left-hand side, you'll take 2 times the left area. So basically when you plug it in and see which side you're landing on, always go towards the tail, and then you'll double that tail area for the 2-tail test. Then for our conclusion, we want to determine is the p-value small or not small. So if the p-value is small, less than alpha, which typically, again, you can assume alpha is 0.05 unless they state otherwise, so that's our significance level. So if the p-value is smaller than that, we will reject the null hypothesis, which means with that p-value, there is evidence for the alternative hypothesis. If the p-value is not small, then we're going to fail to reject the null hypothesis, which means with that p-value, there's not enough evidence for the alternative. So this is where the wording, it doesn't look like it changes much, but it does completely change our conclusion in that having evidence, so we've proven the alternative, or not having evidence, so we can't prove that alternative hypothesis. All right, so let's try this out with some examples. So we have a current antacid. So we kind of seen the setup of this, but now we're going to put it all together. So we have the current antacid provides relief for 70% of people who use it. They have a new drug and they want to test whether it is more effective. So that right there is wording for the alternative hypothesis. Then they run a study with 100 randomly selected patients and 75 experienced relief. This right here is our sample data. So we have our sample data coming through there. And we want to see, is this evidence that the new drug is better? So some pieces that we're getting here, we're getting the setup for the null and alternative hypotheses. Specifically the alternative hypothesis. We want to prove that it's more effective. So as we talked about in the previous video, that's to show that the proportion of people getting relief from the antacid would be significantly more than 70%. And we would assume this drug is at least as effective, so we'd assume it is at 70%. So then from there, we can check our conditions. So we want to check independence, which will say yes, and randomization. We should have a random sample, which we do. And then success failure. So we're going to take our sample size, which was 100, and multiply that with our null hypothesis value, which is 0.7, and then 100 times 0.3. So we're getting 70, 30. So both of those are more than or equal to 10. So we are all good to go. So now what we can do is set up our sampling distribution, and then I'll go ahead and show the work for finding the test statistic as well. So mean, we're just going to look at our null hypothesis, which was 0.7. Standard deviation, take the square root of 0.7 times 0.3 over our sample size of 100. So I'm going to show you the steps for plugging everything in the calculator too, just so we don't miss anything. So this will be square root, separate 0.7 times 0.3 over 100. So it has a standard deviation of 0.0458. Then if we needed our test statistic, so that's our z-score, so that'll come from taking our sample proportion. So our sample proportion, they told us, was 75 out of 100. So a 0.75. So for our test statistic, we're going to take that 0.75 minus our mean over our standard deviation. And we'll plug in all of that at once for accuracy. So our test statistic, let's go ahead and separate 0.75 minus 0.7 over our square root and fraction and plug everything in. And that'll be a 1.0911. All right, so now what we can do is go and calculate our p-value. So we're running a right tail test with this, and how I knew that was checking that what symbol am I using in the alternative hypothesis. So we're trying to prove that the proportion is larger, so that's going to go off to the right-hand side. So in terms of a picture, what we're doing here to find p-value is we have this cutoff, and we want to find the area to the right, and it's that area under the curve that will make p-value. So just to show you the two different ways to go about it, and both will give you the same, if not very similar, solution for p-value, you can use your sampling distribution. And then what you can do is once you set up that sampling distribution, see where your sample proportion lands. So what we'd be using there is this graph would be centered at 0.7, and then I want to see what's the probability of seeing 0.75 or larger, basically our sample statistic or more extreme. So with that, I'll go to GeoGebra, have a standard deviation of 0.0458, mean of 0.7, and I want to find the probability of being at 0.75 or higher, and that's a 0.1375. So with that process, I don't actually use this test statistic at all. It's a way of getting around the test statistic by using the direct distribution that we're working with and comparing our sample statistic. But what we could do is switch to a distribution, our standard normal distribution. So centered at 0, standard deviation of 1, and what it would be the equivalent of is plugging 1.0911. So we could have done this with mean of 0, standard deviation of 1, and then at least 1.0911. And we're off at the 4th decimal place, but that's not a big deal. It's not a big difference. Very, very close, and that it's just due to rounding errors, but same answer. So either way you want to go about it is completely fine. I keep including the test statistic in there just so that you see it, but we could ignore it through the process and get to the correct answer. All right, so we found the p-value, but now what we need to do is figure out, is that p-value small or not small? So what we're going to do is take the p-value, and then we're going to compare it to our significance level. So significance, and they're not saying anything about significance level up here, so what we could assume is we're using a significance level of 0.05 since they didn't specify otherwise. So with that, we just need to figure out which is larger. Again, if it helps, you can change it to percentages. So like this is 13.75% compared to 5%. So our p-value is bigger. So the p-value is not small, which means we are going to fail to reject the null hypothesis, which means there is not enough evidence for the alternative. All of that falls through just because we're using the larger symbol there. So for the conclusion, what I'm going to write out is fail to reject the null hypothesis. Then with a p-value of 0.1375, there is not enough evidence and then I want to grab wording in context for the alternative hypothesis. So let's see, it was all about proving this larger 0.7. What I could do is, if I go back to that wording of test whether it is more effective, well, that's what we failed to prove. There's not enough evidence that it is more effective. Or we could even use this wording that the new drug is better. We could grab something like that. So I would say there's not enough evidence to conclude the new drug is better. And there's a full hypothesis test. So stating our null and alternative, checking the central limit theorem, setting up our sampling distribution, finding our test statistic if we need it, Calculating p-value using that sampling distribution. So there I was using a normal curve centered at 0.7, standard deviation of 0.0458, and then in GeoGebra looking up what's the probability of being at our sample statistic, so that 0.75 or larger. And then once you get that p-value, it's just a matter of is it small or not, which requires comparing it to 0.05 in this case. So we failed to reject, so there's not enough evidence. So long process, but if you follow the steps and follow the formula, it all ties together. Let's do one more example here, and this time I kind of left the space blank so we can go through the process without the guidance of it. So a company develops what it hopes will be better instructions for its customers to set up their smartphones. Their goal is to have 96% of customers succeed. The company tests the system on 400 people, so we have our sample size there, of whom 376 were successful. And in fact, at this point, let me go ahead and write down our sample statistic at 376 out of 400, which should be 0.94. So we have the sample data, and then is this strong evidence that the new system fails to meet the company goal? So again, if you see this word evidence, what follows is going to deal with the alternative hypothesis. So first step here, null and alternative. P equals P. All right, so their goal is to have 96% of customers succeed, and we want to show that the system fails to meet that number. So what that would mean is a lower success rate. So we want to see if the system has a lower success rate than their goal of 96%. So we want to prove, so this is our alternative hypothesis, we want to prove that that proportion of people successfully setting up their phone is less than 0.96. Which means we're going to assume they're reaching that 0.96. We're going to assume they're meeting their goal, but we want to see if we have evidence that it's significantly lower. Because what we can see here is 94% are successfully doing it. So is this significantly lower than their goal of 96%? All right, then our second step, we're going to check independence, which will say yes, and randomization. We'll go ahead and say yes, even though it doesn't say we have a random sample, we'll assume we're good there. Then success failure. So taking our sample size of 400 times the 0.96, sample size of 400 times 1 minus that value, which would be a 0.04. So we're going to have is 384 and 16. So both of those are more than or equal to 10. So we're all good to go there. So there's our first two steps. Now that we pass the central limit theorem, we can set up our sampling distribution. So mean of the sampling distribution would be 0.96. Standard deviation, take the square root, 0.96 times 0.04 over our sample size of 400. So just going to our calculator to plug that in. Let's go square root, separate our fraction, and then 0.96 times 0.04 over 400. So a standard deviation of 0.0098. So then from there, what we're going to do is, and in fact with this one, I'm going to let's find our test statistic. But if you're doing this and they don't specifically ask for the test statistic, in fact, let me go through the rest of this process here and just get to the answer. Sorry, I know I'm deciding mid-video what to do here. And then I'll go and show you how to find that test statistic for more practice at the end. But if you're going through this process and they don't directly ask for the test statistic, what we could do here is go on to the next step to find our p-value. So what we would do is we have our distribution with our mean and standard deviation centered at 0.96. And then looking at our alternative hypothesis, this is our left tail. So 0.94 would land over to the left-hand side here, and we want to find the area to the left of it, and that would be our p-value. So what I'm going to do is go to GeoGebra, plug in my mean and standard deviation, and then find this area to the left of 0.94. So let's go 0.96, and then 0.0098, and then we want area to the left, and then we're going to plug in our 0.94, and we can get this 0.0206 out. So we got our p-value, then we just need to see, is that small or not small? So we're going to compare it to 0.05. Again, if it helps, think of that as 5%, and our p-value is 2.06%. And what we can see in this case is our p-value is small. So our p-value is small, which means we are going to reject the null hypothesis, because essentially what happened is this 94% had a very low probability of occurring if that 96% was true. So what we're seeing is something that's significantly lower than 96%. In fact, instead of looking at my picture in GeoGebra, you could see where our sample landed is in an unlikely territory when we're really expecting to be close by to 96%. So what this would suggest is by them seeing something so significantly far away, this probably isn't the distribution for our samples. For us to randomly select something out here only had a 2.06% chance of occurring, which means our population is likely doing something else. So what we want to do is essentially reject this curve, which this curve represents our null hypothesis. So we're going to reject that null hypothesis, and we have evidence for the alternative that we're actually seeing something much lower than 96%. Now this is where you might see like 94%, it doesn't seem that far away from 96%. But what's happening, and it can be effect of sample size, we have a very large sample size in this case. So to take such a large sample size and see something even a little different can become very significant. Because when we take such large sample sizes, I mean, you can see it in our standard deviation, we expect to be very close to 96% here. So being even just 2% away is a statistically significant difference. All right, so our last piece here would be, we're going to reject the null hypothesis. And then we will say with a p-value of, to state our evidence, 0.0206, there is evidence. And then our alternative hypothesis, I'm just going to kind of reread up here, is this strong evidence that the new system fails to meet the company goal? So yes, we have evidence that the new system fails to meet the company goal. So evidence the new system fails to meet the company goal. All right. So there is another hypothesis test with a little less structure to it. And then just to throw in at the end here, if we needed that test statistic, but you could see it is a step we could skip over. What we would do is z equals, take our sample proportion, which was the 0.94, minus our mean, and then divide by our standard deviation, and plugging that into our calculator just another time so we can see it. Separate your fraction, have the subtraction of your sample statistic minus the mean, and then our standard deviation calculation, which I forgot to separate that, but it'll work out to be the same. In fact, I'll make it clear there, sorry. So separate your fraction. You'll see this works out to be the same. That underneath the square root is all multiplication and division. So in terms of order of operations, it's all pretty equal. It's 400. So negative 2.0412. So if you wanted to use that standard normal curve, that would be the number you would plug in as kind of this cutoff for the left-hand side. So those are some full hypothesis tests there.